I'm Anil Kumar, and in part 2 of trigonometry summary, I'm going to discuss with you trigonometric ratios for all angles, and we'll take up a very special example to find exact value of sine 120 degrees minus cos 210 degrees divided by sum of tan 330 and secant 135 degrees. Now, the main thing which I'm going to address here is cofunction identities, and this exact value will be found using cofunction identities. So it is just a summary, it is not to give you the basic insight to it, but in short, we'll recall what we have learned so far about trigonometric ratios when we are talking about all the angles. So in a coordinate plane where I'm representing x-axis by capital X and y-axis by capital Y, I'm actually representing a point here with small xy. Right, so any point here is being represented by small xy. The idea is that if I transform or reflect this point about x-axis and about y-axis and about x-axis, what happens? So if I reflect this point about y-axis, that is, if I'm reflecting it right there, I get a point here where the coordinates of x becomes negative, so it becomes minus x, but y remains same, correct? If I reflect it on the x-axis, I do get a point here which will have x coordinate same as x, however the y becomes negative. Do you see that? And if I reflect this coordinate point along the, let's take this ink, okay, or maybe this one. Okay, this is good. So if I reflect it about the origin and get to a point here, I get a point which is both negative, right? So kind of like this. So that means this point could go around the circle anywhere, correct? We're talking about trigonometric ratios where we say that we have to work in a right triangle, correct? We are working in a right triangle. So let me join the side and make a right triangle. So I'll join with origin the point xy and we form a triangle. There you go. Now this is the basic triangle with which we have been working all throughout. So let me call this point as O, the origin, and this point as P, and its reflections as Q, R, and S. Now if you look into the triangle, and let's call this point as, let's use ABC. Okay, so A here, and when I make a triangle there, I'll call this point as B. Okay, that should be enough. Okay, so we have different triangles. We'll first consider the triangle in quadrant 1. So this is called quadrant 1, correct? This is quadrant 1, this is quadrant 2, quadrant 3, okay, let me write here, and quadrant 4. So in quadrant 1, we are considering the triangle POA. Let me recall that the ratios which we talk about are sine, which is sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent, correct? Now if I write these ratios for the triangle given in quadrant 1, which is triangle POA, then we can write sine of, let's say this angle is alpha. We'll just call it alpha, right? Okay. So this angle is alpha for us. So sine of alpha is the ratio of the opposite side, which is y, over OP. Now OP basically will be, let's call it R for time being, right? So we'll consider always OP, this length, as positive, correct? So we'll write sine alpha as y over r. So in this triangle, let me write r is equal to square root of x square plus y square. Now, as you know, square root is always positive, right? So this is always positive. It could be in any quadrant. This is very important to understand. Okay, square root gives you always a positive number. And it's a length, a distance. Distance from origin to point P is r. So in this coordinate plane, whether this r is on left side, right side, or facing northwest or northeast, it will be treated as positive. Okay. Now in this particular quadrant 1, what we get here is sine alpha is y over r, cos alpha is x over r, tan alpha is y over x. These are lowercase, correct? Now all are positive. So let me write down here the sign of these. So all of them are positive. All of them are positive. So this is what happens in quadrant 1. So in quadrant 1, we learned this last time. Now let's look into quadrant 2. In quadrant 2, what happens? So you can actually pause the video, write down what sign do you get for these. So in quadrant 2, we get sine. So let me make this triangle here. Okay. The angle actually becomes that much. Do you see that? Angle becomes that much, which is, we'll call this as 180 degrees minus alpha. Do you see that? So angle is always considered to be counterclockwise from x-axis. So let me write down a note here. So note is positive angle is measured as counterclockwise from a positive x-axis. Correct? So that is the angle. So it is 180 minus alpha. Correct? Now, many students even don't understand why we write 180 minus alpha. Now, I hope that is clear. So now we are into the triangle OQB. So now we are considering the triangle OQB. Do you see that? And we are in quadrant 2. Correct? Now, in this quadrant, y value remains positive, however, x becomes negative, and that changes few figures here. So what we get here is, consider that point. So we have a point which is minus xy this time. Okay. So x value remains same. It is y over r. Cos of 180 degrees minus alpha is minus x over r, and tan of 180 degrees minus alpha is y over minus x. Do you see that? So what we notice here is that sine remains positive, however cos and tan becomes negative. Correct? So let's move on to quadrant 3. So as you move to quadrant 3, now that means you're looking into the triangle, which this time is triangle OBR, right? So it's triangle OBR. Now in this particular triangle, the point which you are considering is minus x minus y. So in that case, the angle is how much? The angle will be sine of 180 degrees plus alpha, correct? Since this is vertically opposite angle alpha, so it adds to 180 degrees. So up to here it is 180 degrees, then you add alpha. So it is 180 degrees plus alpha. And then we have cos of 180 degrees plus alpha, tan of 180 degrees plus alpha, right? And when you measure these, using both negative values, we find that sine is negative, cos is negative, however, tan remains positive because both negative quantities makes it positive, right? They cancel. So these two are negative, but that becomes positive, correct? Now if I move on further to quadrant 4, which should be the triangle OAS, we are talking about the coordinate point where x is positive, y is negative, r is always positive, correct? So in this particular triangle, sine of the angle now, this is alpha for us, that's the acute angle. We always call this as a related acute angle. So we'll refer alpha as related acute angle. Is it okay? Now, the principal angle is what I'm writing here. So I'm writing a principal angle, let's call that angle as beta, and all this is kind of beta, okay? So the principal angle beta, that means in this case, should be written as 360 degrees minus alpha, cos of 360 degrees minus alpha, tan of 360 degrees minus alpha. Now if you check their signs using what we did so far, I think you can clearly see that sine is negative, but cosine is positive, and tan is negative, right? Since the y value is negative, that and x is positive, and sine is the ratio of y over r, which is positive, cos is x over r, which is positive, r is positive, let's go back, sine is minus y over r, which is negative, cos is x over r, which is positive, tan is ratio of these two, one of them is negative, so tan is negative. So with this, we have a very standard rule, and that is to say that in our coordinate system, in quadrant 1, 2, 3, and 4, the sign of these trigonometric ratios are, all are positive here. Sine is positive in quadrant 2, tan is in quadrant 3, and cos is positive in quadrant 4. So all students take calculus, all silver teacup, or the cast rule as followed in different continents. You can try to remember any one of these. Okay? You also observed one thing here. This is the cast rule, or whatever rule you call, is that the values could be, once I complete the circle and go back, I come back to xy. Do you see that? And that is the reason why we also call them as circular functions. Right, they are called circular functions. And now, if I sketch these functions with all different values, starting with the first value, you will find that the sine and cosine could have values like this. So that is the sine curve. Sine alpha, when alpha changes from 0 to 360 degrees, right? After this, it repeats. If I consider the cosine wave, then the function which I get, or the graph which I get, will be kind of like this, where this is 0, this is 360 degrees, and all these points are actually 4 quadrants. These are 4 quadrants, right? So it is 90 degrees, 180 degrees, 270 degrees, and 360 degrees, equally divided. If I have to sketch the tan of these angles, let me now make it something like this. What you notice here is, this is for cos alpha, this is for tan alpha. Tan alpha, I'll write this as a ratio of sine alpha over cos alpha. So if cos is 0, something divided by 0 is not defined, and at that point we have a vertical asymptote. Do you see that? Vertical asymptote. So I'll also extend it to this side. So we do have a vertical asymptote at minus. Minus means going backwards in this direction. You get the point, right? So the graph for tan will be like this. Do you see that? Kind of like this. So what you notice here is that the graph of tan repeats from minus 90 degrees to 90 degrees. So it has a time period of 180 degrees. Let me just shift it a bit. Okay. So now let's talk about time period. I'll add one more information here before ending. So we'll call a very important parameter here is time period. For sine, it repeats after 360 degrees. Cos repeats after 360 degrees. However, tan repeats after 180 degrees. Correct? And for sine and cosine, the range is from minus 1 to plus 1. So this is plus 1, this is minus 1. This is plus 1, this is minus 1. But for tan, it could take any real numbers. Do you see that? Right. So these circular functions, they are periodic, and the period for sine is 360 degrees, the period for cosine is 360 degrees, the period for tan is 180 degrees. Sine is positive in quadrant 1 and quadrant 2, cosine is positive in quadrant 1 and quadrant 4, and tan is positive in quadrant 1 and 3. So that gives you basics for trigonometric ratios when all angles are considered, along with some relations here. Correct? And all these are related to angle alpha, which is being called as a related acute angle, and will soon replace 180 minus this, 180 plus this or that with beta, and we'll call that as a principal angle, or sometimes theta general, right? So sometimes theta, which will be treated as the principal angle. So I hope this part is very clear. Now we'll move on to the next part and talk about cofunction identities, right? So I hope this part is very clear to you. Now we'll discuss cofunction identities and move forward. Now let us discuss cofunction identities. What we have learned so far is that when we talk about trigonometric ratios for any angle, we say that all are positive in quadrant 1, sine is positive in quadrant 2, tan is positive in quadrant 3, and cosine is positive in quadrant 4, right? So this is what we have learned so far in the previous part. We also seen why. Now in cofunction identities, we are trying to relate sine with cosine, cos with sine, and so on. Now again, we'll consider the triangle in quadrant 1. So let me now make a triangle in quadrant 1. Let's do it here. So let's make a triangle in quadrant 1. Let's say that is the triangle. It's the right triangle. So whenever we talk about trigonometric ratios, we take right triangles. Let's call this as OPQ. Now, if I change the angle, that is, if I rotate, so cofunction identities normally will be considered when we are rotating. So when there is a rotation about origin. So consider like this, when we are trying to do some rotation about origin, and in first case, I will rotate this angle so that we get another triangle which is kind of like this. So I'm calling this point as P dash and this point as Q dash. So in case 1, let's say A, we have a rotation so that if the initial angle was a related acute angle alpha, now what is the angle? Now this is alpha. Do you see that? That is alpha, right? So that angle here is 90 minus alpha, correct? So if you see the relation between the two triangles, we are now considering the triangle after a rotation. So we'll see what is sine 90 minus alpha, what is cos 90 minus alpha. What is tan 90 minus alpha? For simplicity, we'll just consider the two sides PQ and OQ as of length A and B, right? So we'll say this is A and this is B. Or you could say that the coordinates of point P are, I will call them as BA now, right? Because I took B along the x-axis. Okay. Okay, I should have written A here. I don't know. Okay, I just wrote. Anyway, so be careful. So that is how it is. So I'll use less of AB, more of description. So when you consider the triangle OP dash, you will see that the length A and B has changed its position. The side which was opposite, which is A in this case, PQ, that length has come as an adjacent. Do you see that? So that has become adjacent side. Correct? So in this particular triangle, what we notice is that sine of 90 minus alpha, which is this angle, is actually P dash Q dash over, let's say this is R, okay, over R. However, P dash Q dash, this longer side, is equals to OQ. So P dash Q dash is OQ, right? So I'm not using AB. Okay, let me just let it be there. So P dash Q dash is OQ over R. So if you check with the original triangle, in that case, OQ over R is actually equals to cos alpha. Do you see that? Is actually equals to cos alpha. Correct? So sine 90 minus alpha is cos alpha. Sine changes to cos. Do you get the idea? Now let's do the same thing here for cos 90 minus alpha. So for cos 90 minus alpha, it is equals to OQ dash over R, which is same as PQ over R, which is sine alpha. Perfect. And for tan 90 degrees minus alpha will be opposite side over adjacent, P dash Q dash over OQ dash. Now P dash Q dash actually is OQ in the original diagram, and OQ dash is PQ. And that is reciprocal of tan, which is cot of alpha. Now what you notice here is kind of change from sine to cosine. Do you see that? So whenever you have a rotation by in this case 90 degrees, kind of, right, times 90 degrees, okay, something which is related to 90 degrees, in that case sine changes to cos, and it actually makes sense. Why? Let's look into our triangle now once again. If I see a triangle with angles as alpha here, let's say this is alpha, then that angle for me is what? Since the sum is 180 degrees, here we already have 90 degrees, so this angle is 90 degrees minus alpha. Correct? Now with respect to alpha, the side which is opposite has become adjacent for 90 minus alpha. So you can appreciate that sine and cosine will flip. Correct? Because now you're looking from the other side. Now you're looking from the other side, not this side. And that is the reason why they always flip. And we have cofunction identities. Correct? So I hope this concept is clear. So whenever you have a case where the angles are of this form, in that case sine becomes cos, cos becomes sine, tan becomes cotangent. Is that point clear? Correct? So I've taken a lot of time to explain this, but I'm closing down very fast on rest of the angles. But I hope you get this point. Now the second thing which we always notice here is In this particular case, we are working with quadrant 1. In quadrant 1, all are positive. Do you see? So in this quadrant, all are positive. And therefore, we have positive signs here. Do you see that? But when we do similar operations in quadrant 2, 3, and 4, all are not positive. So if I do something in second quadrant, sine will remain positive. In quadrant 3, tan is going to remain positive. In quadrant 4, cosine is going to remain positive. Is that concept clear? Is that concept clear? Now that is what is most important. Okay, so take your time to digest this much. Now let's get back to quadrant 2. So this part is clear, right? In quadrant 2, we are talking about sine 90 degrees plus alpha. So the triangle which we have is kind of like this. So we are switching from a triangle which is lying down to the one which is standing up, kind of like this. Do you get an idea? And the angle which we are now talking is not alpha, but related to alpha, it is 90 degrees plus alpha. That is what I mean. So obviously, since my triangle has tilted, sine changes to cos, and the angle will say alpha. Since sine is positive, this will remain positive. You get an idea. But if you're looking for cosine of 90 degrees plus alpha, that changes to sine. However, the sine should be negative because cosine is negative here. Got it? For tan of 90 degrees plus alpha, tan is negative, so I should get a negative value, but tan changes to cotangent. You get another set of formulas, correct? Now let me continue with 90 degrees, and this time I will do for 270, this is 270 degrees, right? That is 180 degrees. This is 0, that is 90. If I this time tilt my triangle to this side, now the position is that angle, and this angle is how much? Well, angle alpha now is here. So if I take that triangle, so we are in quadrant 3 now. So in quadrant 3, if I write sine 270 degrees minus alpha, what should it be? Cos 270 degrees minus alpha should be equal to what? And tan 270 degrees minus alpha should be equal to what? So first step is very clear. Sine becomes cosine alpha, cos becomes sine alpha, tan becomes cotangent alpha. As far as sine is concerned, in quadrant 3, only tan is positive. So we keep positive and negative for others. Does it make sense to you? Easy to remember, correct? Easy to remember. Perfect. Now the last triangle, of course, will be 270 plus alpha, correct? I'll save this space for 180 degrees, and therefore I'll actually finish it off here with just a minute. So we could have a triangle like this, where the angle will now be what? Now we're talking about sine 270 degrees plus alpha. Since we are in quadrant 4, that should be negative of cos of alpha. But if I say cos of 270 degrees plus alpha, cos is positive, so it will be positive sine alpha. Does it make sense? And for tan 270 degrees plus alpha, it should be negative cot alpha. Does it make sense? So we just summarized all this when we are treating rotation with respect to 90 to 70 degrees. Correct? Now in this small space, I will draw your attention towards triangle where we are going to rotate them by 180 degrees. Now that's a very simple case. If I have a triangle kind of like this, and if I rotate it, let us say kind of like this. You see these two sides are equal and this side is equal. So sine remains cosine, cos remains sine. Perfect. Now this rotation could be done in any of these triangles, correct? Or could be, let's take some other ink here. Okay, maybe this. Now you always see that base remains base, opposite side repeats opposite side. However, the coordinates of x and y changes, so it becomes minus xy. Here it is both minus, is it okay? And here we have x positive, y negative. The r value remains same, correct? So whenever we are doing these kinds of rotations, these are not cofunction identities, right? These are not cofunction identities, but just a summary to give you that if I do sine of 180 degrees plus alpha, it remains sine. Do you see that? But since we are in 180 degrees plus alpha, we are in quadrant 2, right? So it becomes negative since we are in quadrant 2. Do you understand? But if I do sine of 180 degrees minus alpha, then it remains positive sine alpha, since in quadrant 1 sine is positive, correct? If I do cos of 180 degrees minus alpha or plus 180 degrees, for both cos is negative, we get minus cos alpha. But for tan, if I do 180 degrees minus alpha, it is negative tan alpha. And for tan 180 degrees plus alpha, it is going to be positive tan alpha. Do you see that? So these are other ratios which are related with rotation. However, these are not cofunction identities. Here you're not switching sine to cosine. Sine remains sine. Only the sign, positive or negative, changes depending on in which quadrant you are. Perfect. Now based on this, we'll take an example and figure out exact value of a trigonometric ratio. I hope you find it interesting and easy to remember or recall. So have a good look. Now we'll just move on to the last phase of this part 2, where we are discussing trigonometric ratios for all angles. Now in this part, we'll try to figure out what is the exact value from the concepts learned so far. So I'll kind of review what we have learned in this video so that you get it all straight. So when we talk about finding exact value, we'll also be considering special triangles. So let me make all the special triangles which we have learned so far. This was done in part 1, correct? So we learned 2 special triangles there, which were 45 degrees and 60 degrees. The values for the 45 degrees one is 1, 1, square root 2. And for 60, 30, 90, it was 1, 2, square root 3. We learned the rule that all are positive in quadrant 1, sine in quadrant 2, tan in 3, and cosine in quadrant 4. Now these are your quadrants, right? 1, 2, 3, and 4. With that and the cofunction identities, we should be in a position to answer this question. So let's copy this question. It is sine of 120 degrees minus cos of 210 degrees, tan of 330 degrees plus secant 135 degrees. Now before getting further, I will like you to work on individual trigonometric ratios. We say sine of 120 degrees. It really means what? Now sine of 120 degrees means that you are somewhere in quadrant 2, correct? So you are somewhere in quadrant 2. Let me take some different ink. And if it is 120 degrees, that means somewhere like this. Is it okay? Where this angle is 60 degrees. And that is 120 degrees. Since you are in quadrant 2, you could write sine 120 degrees as equal to, the acute angle is 60. Do you see that? In terms of acute angle. So you could write this as sine of 60 degrees. Do you see that? So we are using related acute angles. In terms of related acute angles, we are doing cofunction identities. And writing all this in terms of related acute angle. Now once you get sine of 60 degrees, you can look into this triangle, which is a special triangle. Sine means opposite over hypotenuse. You get a value square root 3 over 2. Does it make sense to you? So we're going slow so that you can understand. Cos 210, let's go back to cos 210 degrees. Now when I say cos 210 degrees, you are in quadrant 3. So 210 will be 180 plus 30, right? So that should be 30 degrees, so that you get 210, correct? So you could write this as cos of 30 degrees. Now cos of 30 degrees, if you look at this triangle, adjacent over hypotenuse is square root 3 over 2. So how are we getting this? We are getting this from our rule, which is SOHCAHTOA. Sine is opposite over hypotenuse, cos is adjacent over hypotenuse, tan is opposite over adjacent, right? The third one here is talking about tan 330 degrees. So I'll take more room here to explain you what I didn't explain earlier. So 330 degrees could be written as tan of 360 degrees minus 30 degrees. Now that is the acute angle which we have been referring to. So that means I could kind of draw my triangle here where it is 30 degrees less than 360. So that is the acute angle. Now in this particular case, you can see that tan has to be negative, right? I'm sorry, 210 was in quadrant 3, so this should be negative. Is it okay? Okay. Yeah. Sorry for that. So 210 was in quadrant 2, therefore minus cos 30. Now here tan is negative, so I should write here as minus. In this particular case, since you are in quadrant 4, tan has to be negative, so it will be negative of tan 30 degrees. Look at this special triangle, opposite over hypotenuse is 1 over square root 3. Is that clear to you? Correct? The last one here is secant. So secant 135 degrees. Now secant is 1 over cos, remember that. So we'll follow the cosine rules. 135 degrees is somewhere in quadrant 2, right? So it could be written as secant. You could write it in two ways. You could either write it as 180 degrees. It's good to write in terms of 180 degrees minus, let's say, 45 degrees. Is it okay? So if I write as 180 degrees minus 45 degrees, I get 135 degrees, correct? So we are talking about a triangle which could be kind of like this. Now here, that is the acute angle, 45 degrees. Secant is reciprocal of cos, so it is negative. So I could write this as negative secant 45 degrees. So you're looking into 45 degrees triangle, 1 over square root 2, when flipped, gives you minus square root 2. Do you see that? Secant is opposite of cosine. So why I did so? Because secant 45 degrees is equals to cos of 45 degrees reciprocal. So 1 over, do you see that? So it is 1 over square root 2 or square root 2. Or you can say it is hypotenuse over adjacent side. Just flip it. So we get square root 2 over 1, which is square root 2. Correct? So this is just to confuse you a bit. Forget about it. Anyway, we got all the values here. So now we can clearly write down what is sine 120 degrees minus cos 210 degrees divided by tan 330 degrees plus secant 135 degrees. Sine 120 degrees, quadrant 2 is positive, square root 3 over 2 minus cos of 210 degrees, quadrant 3 negative, negative square root 3 over 2 divided by tan of 330 degrees, which is right there as, I forgot to write minus. So since you are in quadrant 4, tan has to be negative. So negative 1 over square root 3. And plus secant in quadrant 2 will be negative square root 2. So you get all this, correct? So here it gets added up, right? Square root 3. So in the numerator, what you get is square root 3. And in the denominator, because half of square root 3 plus, they add up to plus, correct? Here both are negative. So what we get here is denominator is common to square root 3. Tan is negative 1. And we'll multiply this by that, giving us negative square root 6. Now when you flip this times this is 3 divided by, we could say 1 plus square root 6, but you can take negative outside. Do you see that? So you could see that this expression results into negative 3 over 1 plus square root 6 as your answer, right? So I hope the steps are absolutely clear and you have understood how to apply the rules to get to the exact values related to the related acute angle. Now, very important to note here is that I really didn't use the cofunction identities. For any angle, you could say 90 plus 45, right? So you could do 90 plus 45 is 135, or you could do 180 degrees minus 45 is also 135. I kind of avoided cofunction. It creates confusion. So when you are doing with exact values, better to use 180 and 360. So let me summarize that in this part of the video, we have learned about all trigonometric ratios when angle could be anything, right? So we could have any angle. So you also understand now, since sine and cosine are circular functions, if I write sine of, let us say 400, let's say 400 degrees, right? So sine of 400 degrees will mean what? Will mean what? It really means that you go one circle, which is 360 degrees, and then come up more 40 degrees. Do you see that? So I could write this as sine of 40 degrees. That is what we mean, that they have a time period of 360 degrees, correct? Now if I say evaluate cos of, let us say 750 degrees, let's say. Okay, now that means what? That means what? That really means that if I have, let me just sketch it again for you. So what we'll do here is we can go one full circle as 360, another circle as 720, and 30 more, and 30 more. So we get to this point where this angle is just 30 degrees. Do you see that? So this is equal to cos of 30 degrees. And from this triangle, cos of 30 degrees is square root 3 over 2. Do you see that? So any given angle can be solved with the help of what we did so far. Now, sometimes we could have negative angles also. So let's say tan of minus, so I put that negative angle. Is that okay? So when I say tan of minus, and let me write down the angle as 360 plus 30, which is 390. Let's say 390 degrees minus, right? So that means we'll go clockwise. So if you go clockwise, this is 360 degrees, correct? And 30 more. So you are here, 30 more. So you are in this quadrant with this as 30 degrees. Since you are in quadrant 4, it will be minus tan of 30 degrees, and that will be, from this triangle, the value will be 1 over square root 3. So it will be 1 over square root 3. Correct? So with the knowledge you've got, you can actually work with any angles. They could be clockwise or counterclockwise. If the angles are counterclockwise, they'll be treated as negative, right? So now you can evaluate. And if you have special triangles, you can find exact values. Otherwise, you may have to use calculator. So in the next part, we'll use calculator to find different trigonometric ratios under separate conditions. Here you learn cofunction identities, and you also see that most of the time we avoid using cofunction identities. Given such problems, we try to relate them with 180 degrees or 360 degrees. Do you see that? Correct? So that's the case. We wrote 120 degrees as this is 180 degrees minus 60 degrees. Do you see that? 210 we wrote as 180 degrees plus 30 degrees to come up with that result. We did not use 90 degrees plus or minus or 270 degrees plus or minus. That is a key. Avoided using cofunction identities most of the time. So I hope with this we can end the video. Look forward to the next one to have few practice questions on what we have learned. Feel free to share your views and comments. If you like and subscribe, that'll be even better. Thanks and all the best.